Welcome to Cosmic Compass, the channel where we navigate the mysteries of the universe together. From distant planets and ancient stars to the cutting-edge technology that makes space exploration possible, this is where curiosity meets discovery. Today, let's take a journey into one of the most overlooked yet vital parts of space exploration: how we talk to spacecraft billions of kilometers away. From the deep space network to the future of laser communications, we'll uncover the invisible lifelines that connect us to the cosmos. Imagine this: a small rover, no bigger than a car, crawling across the dusty red surface of Mars. It is more than 360 million kilometers away, and yet almost every day we receive images, videos, and streams of scientific data from it. That rover is Perseverance exploring Jezero Crater, and if that sounds impressive, think about Voyager 1. Back in 1990, it turned its camera toward Earth and captured the famous pale blue dot image from nearly 6 billion kilometers away. At that distance, Earth was nothing more than a single pixel in the vastness of space. How do these spacecraft, separated from us by such staggering distances, stay in touch with Earth? Right now, all of this communication depends on radio waves, the very same type of waves that carry music to your car radio. But out there, in the emptiness of interplanetary space, these signals weaken and the data transfer speed drops to levels far slower than dial-up internet. This is one of the greatest challenges of space exploration. If our probes can only whisper back home, how much science are we missing? Today, let's explore how NASA has overcome these limits, how we communicate with spacecraft billions of kilometers away, and how a new technology may revolutionize deep space communication. When we think about communication with spacecraft, it's easy to imagine a powerful antenna on the probe itself, beaming signals across the solar system. But the truth is, those spacecraft are too small and too fragile to carry such enormous equipment. Instead, they rely on compact directional antennas, efficient, yes, but far too weak to send data on their own over such vast distances. That's where Earth steps in. Most of the heavy lifting happens here thanks to one of the most important and often overlooked pieces of infrastructure in space exploration, the Deep Space Network, or DSN. The DSN is the largest and most sensitive scientific telecommunications system in the world. Since the dawn of the space age, it has been our link to the cosmos. It was the DSN that received and relayed the first live TV images of Neil Armstrong taking humanity's first step onto the lunar surface in 1969. It was also there for Apollo 13 when a ruptured oxygen tank turned a routine lunar mission into a desperate struggle for survival. During re-entry with the crew using minimal power to keep their spacecraft alive, there was hardly any energy left to send signals home. And yet the DSN managed to capture those faint whispers from space, helping guide the astronauts safely back to Earth. Even today, every single NASA spacecraft beyond the moon rovers on Mars, probes around Jupiter and Saturn, and even Voyager, at the edge of interstellar space, remains connected to us through this network. But how does it work? The DSN consists of 3 facilities placed strategically around the globe, one in California, one in Spain, and one in Australia. Each site is roughly 120 degrees apart in longitude, which means that as Earth rotates, at least one station can see any spacecraft at any given moment. These sites are also located in semi-mountainous terrain to shield them from radio interference. Each complex houses multiple giant radio antennas, some as wide as 70 meters. Together they form a worldwide system that can receive multiple incoming signals at once. But there's a limitation: each antenna can only transmit to one spacecraft at a time. Through this system, the DSN sends commands, uploads software, and receives the precious data collected by our robotic explorers. It even supports other space agencies like ESA in Europe, JAXA in Japan, and ISRO in India. Truly, it's a global bridge to the stars. As impressive as the DSN is, it comes with serious challenges. The antennas are enormous, expensive to build and maintain, and some are now decades old. Replacing major components can take months, during which time a vital antenna might be offline. The oldest 70-metre dishes are already reaching the end of their lives, but the biggest limitation is speed. At interplanetary distances, even with DSN's vast antennas and ultra-sensitive receivers, data transfer is painfully slow. Let's put this into perspective. After its historic flyby of Pluto in 2015, the New Horizons spacecraft took more than 2 years to send back all the images and measurements it had collected just from that single encounter. So while we dream of high-definition video streams from the outer planets, the reality is that right now every bit of data trickles back at an agonizingly slow pace. It's like trying to download a movie over a connection slower than 1990s dial-up internet. Clearly, if we want to explore the solar system in richer detail, we need something better. This is where NASA's Laser Communications Relay Demonstration, or LCRD, comes in. For decades, radio has been our only option, but what if, instead of radio, we used light in the form of infrared lasers carries far more information than radio waves? Imagine the difference between a bumpy country road and a modern multi-lane highway. That's the leap optical communication promises. Launched in December 2021, the LCRD is NASA's first dedicated test of space-based laser communications. From its position in geostationary orbit, it can send data to Earth at up to 1.2 gigabits per second. To put that into perspective, that's like upgrading from old ADSL internet to fibre optic broadband. The advantages don't stop there. Optical instruments are smaller and lighter than radio hardware. That means spacecraft using laser communication can save mass and volume, allowing more room for scientific instruments or simply reducing launch costs. The entire LCRD payload is only about the size of a king-size mattress. Compare that to the DSN 70-metre antennas towering like steel skyscrapers, and the difference is striking. Laser communication systems are also more power efficient, squeezing more data out of less energy. For a spacecraft operating on limited solar panels, that's an enormous advantage. But there is a catch. Unlike radio waves, laser signals cannot easily penetrate clouds. That means NASA must carefully choose ground stations in places with minimal cloud cover. For the LCRD demonstration, the signals are being sent to California and Hawaii, both locations chosen for their clear skies. So what exactly will LCRD do? One of its first applications is improving communication from the International Space Station. Right now, the ISS is only visible to ground antennas for short periods during each orbit. But if it can relay data to LCRD in geostationary orbit, then suddenly those windows are much longer and the speed is far higher. But the real excitement comes with upcoming missions. In 2024, NASA plans to launch Artemis II, the first crewed mission around the moon in over half a century. With laser communication, the astronauts will be able to send ultra-high definition video back to Earth. For the first time, we may watch humanity exploring the lunar surface in breathtaking clarity, as if we were standing there ourselves. Then in 2026, the Psyche mission will journey to a metallic asteroid more than 240 million kilometers away. On board, it will carry the deep space optical communication payload testing laser technology at interplanetary distances. If successful, it will prove that even far-flung missions can rely on laser links, opening the door for future probes to stream back science faster than ever before. These advances promise to remove one of the greatest bottlenecks in planetary science, the time it takes to receive data. Imagine watching high-definition video from Mars, or even live streams from the moons of Jupiter. That might sound like science fiction, but with optical communication, it could soon become a reality. Deep space communication has always been the invisible lifeline of space exploration. Without it, every rover, every probe, every astronaut would be lost, cut off in the void. For decades, the Deep Space Network has served as our voice across the cosmos, capturing faint signals and turning them into discoveries that changed our understanding of the universe. But now we stand on the edge of something new. With lasers, we may soon bridge the gulf of space faster and more efficiently than ever before. Missions will no longer trickle their science home. They will flood us with data, letting us see distant worlds in ways previous generations could only dream about. So, as we look ahead to Artemis Psyche and beyond, let's remember every improvement in communication is more than just technology. It's a way of bringing the universe closer to us, of making the distant familiar. And who knows, the next time we see a rover's journey across Mars or a probe's flyby of a distant asteroid, you may not just be looking at static images years after the fact. You might be watching it unfold in real time from the comfort of your own home. That brings us to the end of today's journey. We've seen how NASA's Deep Space Network has carried our voice across the solar system for decades, and how new laser technologies may soon transform the way we experience the universe. If you enjoyed exploring with us, don't forget to like this video and subscribe to Cosmic Compass so you never miss a chance to journey deeper into space. Until next time, keep looking up, because the universe is waiting for us to discover it.